I'm Shreya, I'm a research scientist at Amazon, and today I'll be presenting my work, which was done in collaboration with Rahul, who is currently at Facebook, and other researchers at Amazon. So I'll be presenting a method to do offer recommendation when they're in the presence of constraints. So just as an introduction, so companies like Amazon, Netflix, Uber, Lyft, like various supermarkets, retailers, they often deal with the problem of offer recommendation, and traditionally this problem, when they deal with it, they have multiple offers to choose from or promotions to choose from, and each of these offers have certain constraints around them. These constraints are usually around the budget of an offer, so there's a limited number of offers you can give out. There are multiple offers, and then there could also be eligibility constraints, which are around which customers are actually eligible to get that particular offer or promotion. And given that this is the situation, how do we best allocate offers or promotions to customers to maximize some kind of a business metric, which could be customer acquisition, retention, etc. So this offer allocation problem can be illustrated as shown here. So here we have 6 offers. Each of them have different budgets. So offer 1 we have only 5 of offer 1. Offer 2 we have 7 of offer 2, etc. And offer 6 has the most budget, so it's 18 offers. And we have 4 customers in this case. Each of them have different capacities, so each customer can get a certain number of offers. So customer 1 can get only 1 offer, and same for 3 customers, which is typically the case we deal with. And customer 4 in this case can get 2 offers. So in this case, a capacity of a customer would be 0 if the customer is ineligible for the offer. So given that these are the constraints, this can be a possible assignment between the offers to the customer. And wherever the assignment is 1, I've only shown those allocations, and the rest is 0. So there are some approaches to deal with this problem. So traditionally you can do this in a greedy manner. So you can find what the likelihood of a customer is to convert. And when I say convert, it could refer to a customer's likelihood to be acquired or a customer's likelihood to be retained. And so you can estimate those propensities at the customer level, and you can greedily give offers to customers until the budgets are met for the offers. Second approach is there could also be bandits which are used for this problem. So bandits for online resource allocation can also be used. So bandits only meet the capacity and budget constraints in expectation. They don't meet it exactly. And sometimes in this problem, if you are dealing with long-term metrics like acquisition or retention, there could be a difficulty using bandits because of the delay in feedback. But there are approaches to deal with that. But the main problem is the constraints not being met exactly. And greedy approaches, the problem with using greedy approaches is since they only handle the constraints downstream, they often lead to suboptimal allocations. We propose a solution in this paper that allocates these offers by optimizing the objective of the business while also meeting the constraints exactly. So to do this, we formulate the offer allocation problem as an optimization problem. So we want to maximize across all customers I and across all offers j. We want to maximize the likelihood of the customer to convert given the offer and given the customer's historical attributes. And this multiplied by the xij, which is the allocation of the offer j to customer i. This is our objective that we want to maximize. And the constraints are also listed as below. So across all offers, a customer can get a maximum of ci, that's the customer capacity. Across all customers, an offer of oj, and only the sum across all customers has to be less than or equal to bj, which is the budget for that offer. And this xij, which is the assignment of the offer j to customer I, is strictly integral in our case and can be 0, 1 until oij, where oij is the maximum number of offers oj that a customer I can get. So under this formulation, we can actually reduce this this problem to a min cost flow. Just as a reminder, so the constraints here are all integral. The constraints are integral, so this is actually reduces to a linear programming problem. And we further write it out as a min cost flow problem where we minimize. So we are minimizing across all customers and offers 1 minus probability of conversion given Fi and Oj. And so so we were maximizing the propensity, and the cost in this case is 1 minus the propensity. And the constraints remain the same. Also, one more point to notice, in our case we have assumed that Ci and Oij are 1, so a customer can get a maximum of 1 offer. And this is related to the domain that we were solving for. Like at Amazon, we usually have only one slot on the page where we can show an offer to a customer, and we can only show one offer. So because we reduced it to min cost flow, we can also leverage algorithms like network simplex algorithm, which typically work orders of magnitude faster than typical LP solutions. This slide shows an example of a min cost flow for 2 customers, V1 and V2, and 3 offers A, B, and C. So, as in a min cost flow, the sum of capacities coming to the node and going out of the node have to be equal. In this case, for the customers, we have C1 and C2 as the customer capacities, and we have 1 minus probability of the offer as the cost of giving the offer to the customer. And then from each offer, we also have the capacity of the offer, so the budget coming out. So across all customers, this is the maximum number of offers that we have given. And so this is the min cost flow solution for. This shows the capacity and the cost for allocating a unit flow across between a customer and an offer. So for illustrating this problem and use case, we have used an example data set, which is a public data set by Hillstrom, which is in the references of the paper. So this data set consists of 64,000 customers who have shopped in the last 12 months. And they were part of an email campaign where they received 1 of 3 emails randomly. One email was about men's merchandise, the other about women's merchandise, and the third treatment was no email. And the overall objective for this data set is to maximize the total visits across all the customers. But as I said earlier, this can also easily be customer acquisition or retention. And the constraints are that at most 10% of customers can get email ME and 10% can get email NE. So the methodology we followed is first we use propensity models to estimate a customer's likelihood to visit given their historical attributes and given each of the emails, which are the offers in our case. And this we did by using an extreme gradient boosting method, but there could be other methods like logistic regression or neural networks which can be used to estimate this. And we use this using the random data which was available in this data set, but in practice we can use A/B test data to build this propensity model. Then this propensity model is fed into our optimization framework where we are maximizing across all customers, and in our case across 3 offers, their propensity to visit given their historical features and given the offer, and across all the assignments as well. Thirdly, we have evaluated this offline in our paper using 4 different offline estimators. And this offline estimator, what it does is it simulates the policy that this optimization technique would produce. It does it offline using the random data that was logged. And there are different methods, each of them have their own trade-offs. So we've compared all the 4 estimators in our results. So here we show the results that we got using our method. So we compare our method, which is optimization, versus 2 greedy approaches. So these 2 greedy approaches are use the propensity models, which estimate the likelihood of the customer to visit given NP and then given WE. And we rank customers based on each of these propensities and keep allocating them emails until the budget for the email is met. And we also compare it to the randomized policy. So if we were to randomly give customers 1 of 3 emails such that the capacity constraints are met. And we show that using all the 4 estimators, which are the direct method, W robust, IPS, and self-normalized IPS, we see that optimization outperforms the greedy approaches using all of these estimators, and it obviously outperforms random. And this data was simulated over 100 bootstrap samples. So even though we see that optimization is outperforming the greedy approaches, there is a caveat to it. So we also did an estimation as to like if the arrival probability of the customer or arrival probability across the entire population as a function that we have plotted the greedy and optimization policies and the visit rate that we got. So here the arrival probability just means the probability that a customer actually opens the email. In practice, it could also be the customer actually seeing the offer or visiting the website. And we see that for lower arrival rates, the greedy approach is actually better than optimization. But as the arrival rate keeps increasing, the optimization outperforms the greedy, and they are cut off at 50% here. We have offered 2 extensions of our method in the paper, and I'm not going to go into detail because I'm almost out of time. So one is this optimization that was proposed before is a single period solution. So we only optimize for a single time horizon, the best offer to show a customer. This is also extended to multiple time periods. You can refer to the paper for more details. Secondly, we also do how to extend this method to be more scalable, where we can optimize not at the customer level, but potentially at the segment level, so over clusters of customers instead. So in conclusion, in this paper we present a net-cost flow-based solution of constraint offer recommendation. We show performance improvements over greedy approaches, and we've also shown 2 extensions for this work, for clustering and then for sequential time period solution. And the next steps are firstly to productionize the optimization algorithm. So currently we have the greedy methods which are in production, but we want to also productionize the optimization solution. When we productionize the optimization solution as it stands today, it will be an offline estimation. So we would have to reevaluate the optimization every single time period, which could be a day, a week, etc. So another next step would be to extend this to an online setting. So can we learn faster? Can we like optimize by estimating customers' arrival probabilities and greedily allocate based on customers who would arrive while also optimizing. And then also we want to implement the sequential time period and clustering solutions to test for scale and performance. And these are the references that we use. Questions?
We have time for some questions. Please raise your hand. Gotta keep these volunteers busy.
Thanks for the time. Can you say a few more words about how it estimates when you go beyond 64,000 users to 64 million users or potentially billions?
So we implemented this for 64,000 customers that are shown here, and then we also implemented it on Amazon data set of 1 billion customers. And then for that, it took about 30 minutes to solve. So if you're doing it offline, it's not too bad. Like you can use the solution. But we do have to test it for larger numbers of customers. And one of the proposed methods, that's why the clustering could be a potential solution if we cannot scale.
Just a point on the clustering side for design in the AAA paper in 2015. It was actually taking that LP formulation, like the one that we presented, and actually creating clusters dynamically using common functions.
Okay, thank you.
Thanks for the talk. So you mentioned how the greeting approach works better when the arrival probability is lower. So on an average, if you take an example of Amazon, the probability of opening an email would likely be on the lower side. So when you do this at a population level of the entire customer base, wouldn't the greedy approach work better?
So if you're looking for a small enough time period, so my application, so even though this was on email data set, like most of the applications we deal with are showing customers offer on site. So, but the problem is still the same. So if we do optimize it, so if we do it for a week at a time, so I think as the time horizon keeps increasing and the customer's probability to arrive increases, we would see over a larger time period that optimization is outperforming really. Yeah.
Thank you.
Any last questions here? All right, thank you.